Everyone, please let me know if I am visible or not. I am facing some internet issues currently. Now those are fine. Can someone please confirm in chat? If someone can confirm quickly, then we can start with the session. Guys, can you please confirm? I am not seeing any messages yet. Once you can confirm, we can quickly start with the session. Okay, I hope I am visible. Okay, let's quickly start with the session. Okay, so all those guys who are live now, can you please comment something so that I know you are able to get me? Okay, so as discussed yesterday, we will be going forward with some more depths in ASIC versus FPGA session. So maybe for those who have not attended the previous session, I can go with some highlights of the session. Please let me know, guys, if you have any doubt or something, because I am unable to see any messages from you guys. Okay. Okay, so this is about me. I'm Pratyush and I have done my master's from IIT Bombay, currently working as ASIC engineer at Nvidia, and this is my journey so far. I am okay. So let's get started quickly. So first we went on why we need to discuss what is FPGA and what is ASIC. So basically, chips are like brains to our gadgets. Just in the way the brain controls all the parts of our body, chips control all the peripheries of the gadgets. Okay, and these chips have many tiny logics. Okay, so yeah, so and but the thing is how these chips are built. Okay, how to build these brains. So here comes the thing of FPGA and ASIC. Okay, thanks. Thanks for confirmation. Okay. So what is FPGA? It's in general a field programmable gate array, and on simple thing, we can take it as some collection of Lego blocks. So from which we can assume to construct something good out of the Lego blocks. Okay, so you can arrange the Lego blocks in some manner and you can produce the required output. Okay, and the good thing with FPGA is they are programmable and they are perfect for learning and testing purposes. Okay, the ASIC, as the name suggests, it is application specific. So, like a custom built robot, it can do only one thing, not any other thing. So you have something in mind, and you from that specifications you make a product, and that is called ASIC. It cannot do any other thing. Okay, the good thing with ASICs are they are fast, they are good enough. Okay, and now where do we use ASIC? So as I already told that FPGA are used for testing purposes and everything. Hi Vikas. So ASIC is used for actually putting these things into the product. Okay. Okay, you have done testing and everything, but you need to put something in the working format, right? You cannot keep everything in testing. So that's where the use case of ASIC comes in. So that was this quick comparison. So today we will deep dive into these things. So I will cover in the next slide, and I hope you guys will find it more uh, comprehensive. Okay, I have tried to bring the best content for you guys, and thank you everyone for joining the live class. Okay, and if I receive a good response, we will be coming up with quite few more knowledgeable session like this, and I would be happy if you would suggest me if I need to take some sessions on some other topic. I am open for suggestions on any topic. Okay, please let me know, guys. Those who are live, or if you are watching offline, then you can comment there. Yeah, thanks. So now today let's discuss internal architecture. अब भाई ठीक है, इसे FPGA डिफरेंस देख लिया, सब जान लिया कि ठीक है ये होता है, ऐसा होता है, इसका इस पे एडवांटेज है. But okay, what is the internal architecture? Okay, how does FPGA or ASIC works? Okay, so this is gonna be very interesting topic, and I will start this topic in 1 or 2 minutes. Let everyone join. Which guys means whoever is interested, and by the time you guys can let me know in some comment section how is this things going, is this session helpful or not, and then I can bring some more sessions like that. I'm waiting, guys. Those who are live, please comment. If we receive good feedback, then we can make more contents more lively. Okay. Okay, then let's start with it. Okay, so in general, what I told is what is FPGA and where to use it. But what is the internal architecture? How the FPGA actually looks like? It's very fancy to say, okay, sir, you said this thing, okay, we can program this FPGA in any fashion and we can easily play with it. But how, as a designer, you can create something which is programmable on some user's end, okay? How did they come up with this idea? Okay, so everything in VLSI or anywhere in the world starts with building blocks. Okay, अगर तुम घर भी बना रहे हो, so you require the building blocks, right? In similar way, FPGAs are made. Okay, you have the blocks, and you can use these blocks in any fashion to get any output. Okay, so let us quickly go through what all things FPGA has. Then I will explain everything in detail. This session is gonna be very interesting, so please stay tuned. Yeah. So FPGA has some logic blocks. Okay, what are logic blocks? Logic blocks are just made of some LUTs, MUX, and flip-flops. Okay. Ambika is asking which is better, more in ASICs or FPGA. Ambika, as I already covered in last session, FPGA is good for testing purposes, for educational purposes, for research purposes, or somewhere where you need more configurability. Let's say you are on a space mission, okay, and in space anything can go wrong suddenly. Then you may need to switch to some alternative, right? So that's where use of FPGAs come into picture, but they are relatively slow. Okay, and ASICs come where we know that this is the direct functionality which we want, and we want to stick to that for the lifetime of the chip. Okay, but we need very high performance, very low power usage as compared to FPGA. That's where ASIC comes into picture. Okay, I hope this clears the question, Ambika. Okay, so these logic blocks, okay, these are made up of LUTs. LUTs are just nothing. So let's say you have some circuit AND gate, let's say. So if you have 1 1, it should give output 1. If you have 0 0, it should give output 0. So this thing you store it in tables. That is LUT, lookup tables. The tables which you will look up according to the input. So if A and B both are 0, then give the output as 0. Similar to these things. These are LUTs. Then MUX, these multiplexers or MUX, which are like bypassing elements. So you have a select input. Okay. So let's say you have a select input, and you have two inputs. So on the basis of select, you can select either of one input line to the output. So those are mux, and flip-flops are nothing, just a storage element. Treat it as a storage element for now. We will cover everything in detail. And those who have done some digital courses, they would already have very good idea about it. Okay. So apart from, okay, now in FPGA, we got logic blocks. Compare them to bricks. Okay. So you have bricks. Now what? You want something to stick the bricks together, right? They can't stand on their own. So that's where the routing matrix is laid out. So our routing matrix is laid out like in the green line here you can see, right? So here the routing matrix is there, and this routing, using this routing matrix, we can use any of this blue. Blue means blue are the logic blocks. So any of these logic blocks we can use. Okay. And in addition to that, okay, so there are many things which people do with FPGA. So there are some requirements of very high level blocks like multipliers, DSPs, PLLs, everything else. Okay, so for that, FPGA designers have kept some hard blocks which can directly be utilized. So let's say in Verilog, you write A into B, right? So that A into B is a multiplier. Now, in synthesis, what will happen is it will get converted into some multiplier logic, and everything will be done in the end. Okay, but if you have some built-in multipliers, so what does the FPGA synthesis tool will do is it will map those multipliers to the built-in multiplier block. It won't use up any logic block, and that will in turn save the memory, and it will make the FPGA more open to user for using the logic blocks for different purposes. Okay. So, and these built-in multipliers will be very fast, means those will be the optimized multipliers. Okay. Sometimes maybe the synthesis tool would not optimize the your multiplier code correctly, but yeah, if it uses the built-in multiplier, it will be very optimized. In same way, there will be different BRAMs, TSPs, PLLs, etc. Okay. So next type of blocks is configuration memory. So consider it as some memory. Okay. What happens is, as I already told yesterday, I think Vikas asked me. Okay. Vikas asked me, sir, how do we configure this FPGA? So that's where this bit stream comes into picture. So what happens is, after I will explain it more in the next slides. After synthesis and everything, FPGA tool stores a bit stream. Okay. And this bit stream is fed so that the routing is done and correct logic blocks are being connected. Okay. And the next last thing, which is more obvious thing, is it has IO blocks. So IO blocks, input output blocks. So let's say if you wanted to build a multiplier and you wanted to give some inputs A and B, then how would you do it? So A, you will give an input to the FPGA, right? So those are the IO blocks. This is where the IO blocks come into picture. So this will map A to input, B to input, and C, which is the output, to output blocks. Okay. So this is in general how FPGA looks like. Please let me know if you get the concept or you want to understand something. Vikas, Ambika, Priya. Okay, let's move to the next session. So here I'll be giving a brief how these logic blocks work. Okay. So let's say you have the input A, B, C, and D. Let's say, okay. So what will happen is, let's say you give a logic. So FPGA synthesis tool will convert it into some lookup tables, and those lookup table it will store inside the logic block that is stored inside the LUT block. Okay. Yeah, Vikas, thanks. So inside the logic blocks, you have LUT blocks. So in those LUT, the FPGA will store the bits. Okay, if the user has this input, then give this output. Okay. Then we have a D flip-flop, which is acting as a memory element. Okay, so you won't lose any data. And then we have a mux, which can either select the delayed version of the output or the output directly. Okay. So let's say you had given something as an input to here, and in multiple clock cycles you wanted to use the output of this single value, then this D flip-flop comes into picture. Okay. In first clock cycle, okay, you can get data through LUT, but in next clock cycle you won't get any input, but you needed some output. Okay, that output is constantly needed. So in that way, the D flip-flop stores it and it gives as an output. Okay, is it clear? If it is clear, guys, we can move to the next section. It is going to be very interesting, since I find it interesting. Yeah. So you guys are getting the flow, right? How the FPGA programs and converts it into some usable logics. Yeah, I see many people live, but they are not commenting. I don't know what's the reason. Okay, guys, if everything is clear, then we can move to next session. Vikas, Ambika, anyone can confirm? Okay, let's move to the next thing. So, yeah, should you please repeat why D? Okay, yeah, I can repeat why D flip-flop is here. Okay, so Bhuvneshwari, let's say you means there was some logic which given the A B C D as an input. Okay, in one clock cycle. Consider it as a in clock cycle number one. Okay, let me use. Okay, in let's say in clock cycle number one, you had some ABC input. Okay, so in this clock cycle number one, you had some ABC inputs. Okay, and in the next clock cycle, this ABC inputs were changed by some logic. Okay, but there is some other logic which is standing there, which needs the output from this logic, this values only in some other clock cycle. Then how will you use it? So you need a storage element which can store output of this thing across the cycles, so that if there is a dependency for some element in the next clock cycle, then this can be used as a memory element. Okay, so this will be just a one clock cycle delayed version of this signal. Okay, so consider it as an output O. So the D flip flop output will be stable until the next clock cycle. Okay, got it? Got it? Mm, yeah, okay, thanks. Okay, then we can move forward, right, guys? Okay, so okay, now you would be like, sir, you have explained us what are logic blocks. Okay, so I know what is inside the logic block right now, but my design works like a synchronizer, not like a synchronizer, Bhuvneshwari. It works like storage element. So let's say if there is a glitch, okay, so you won't lose the data, right? Let's say there is some glitch or there is some unwanted change in the input, because the inputs will be synchronized throughout the clock cycle. Okay, so you can tell it it's not a synchronizer, because synchronizer basically I can explain the concept. So what happens is, let's say you have a flop. Okay, so let's say this flop is getting the clock 1 and this flop is getting the clock 2, and these clocks are different across the domains. Okay, so these clocks have some phase differences and the frequency differences also. Okay, then if you want to transfer some data to this flop, then there is a chance that you may miss the data, right? So that's where we put the synchronizers. Synchronizers are used to go from one clock domain to another. Okay. And here I am talking about the uh, change, like storing element. So I want to store the output of this LUT for one clock cycle so that everything is good, means I don't miss something. Okay. Clear, Bhuvneshwari? Okay. Yeah. So, huh. So, okay, you guys must be wondering like, is this? Huh. Key. Okay, sir, you talked about the CLBs. So I have some logic stored here, some logic stored here. FPGA is very big, as as you said, like some logic is here, some is here. Let's say I made a logic, so one logic is here, one is here, one is here, and one is here. Now, what to do? How would I connect everything? Okay, so that's where this what we say interconnects come into the picture, right? So how are these interconnects working actually? Now I will explain how these works. Okay, so this have a simple switch. Okay, so let's say this CLB wants to connect to this CLB, then you can just simply turn on the switch. It's as simple as that. Okay, and how these switches are programmed? So these switches are programmed according to the bit stream, which is fed in. Hmm? Now I will talk more about how the bit stream is generated. Okay, so yeah, so if this is clear, this is very simple. Okay, so if this is clear, please let me know. And if you have any question, please comment. Bhuvneshwari, Vikas, Priya, anyone. And thanks guys for being so active in the section. Okay. 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 So this is more like a better representation of what we have done. Switch is basic mux-based architecture. Oh, yeah, circuit construct. No, it's not a mux-based architecture. These are normal switches, which there are many different kind of switches. So yeah, that we can cover in some other session. Yeah, switches are just for routing purposes because yeah, but there are many different types of switches which can better than mux actually, which can quickly connect and reduce the wire delay actually. Okay, so those are all custom switches just for your information. Circuit construct. Okay, so currently consider it as in black box having a switch, but yeah, those are not mux based. There are many better architecture which are available. Yeah, switches are just for routing purposes. Yeah, more or less you can say that these connects the logic block. Okay. So now this is just a similar to what I have covered, but now we can give like a summary. So let's say you made a very complex design which has some multipliers, adders, some memory elements to stored, some logic. Okay. So what will happen is if you have some memory elements, it will get stored in the volatile memory. And if you have instantiated some adders, multipliers, some floating point adders, let's say some fixed point multipliers, something else like that, very complex. So if the FPGA supports some hard macros of this kind, then they will be instantiated in these kinds of block, and rest all whatever logic you have written, that will be constructed inside the logic cells, and the switches will be programmed in such a manner that each block can communicate to each other, okay, as required. So there may be a possibility that logic cell on the left side and on the right side don't need to communicate at all. So that's okay. FPGA will program like that, okay? That's not our issue. Okay, so guys, if everything is fine until now, we can move to the next topics. तो भाई अब अपना जो FPGA है वो बिल्ड हो चुका है लाइक वर्चुअली. तो अपने पास ब्रिक्स थी, सीमेंट थी, and we had some different kinds of bricks as well. So now, yeah, now let's give the finishing touch. पुट्टी करा लेते हैं. Please confirm, guys, if everything is fine or you have any questions. Okay, I guess we can move forward. So, yeah, okay. So the last thing is IO blocks. Oh, thanks, Vikas, thanks, Bhuvnesh. So last thing is IO blocks. Okay, so what happens is, okay, you have the logic and everything, but how you will take the input and the output, okay? So for these IO blocks, you have something called a tri-state buffer, okay? So let's say you have a output, hmm, or an input. So until your output is ready, or until you don't need the next input, you don't want the pins to get connected, right? So that's where the tri-state buffer comes into picture. So keep it as simple. Tri-state means on, off, floating. Okay. So if it is in third state, it is floating. It is not connected at all. So it is a high impedance node. Okay. So it won't cause any trouble to the interface outside. So it is just a buffer. Okay. So is it clear? So if it is not in the third state, means not in the high impedance state, then it will directly pass on the whatever data input to the internal pins or internal pins to the output. Okay. I don't think here we should have any question, but yeah, please shoot if any. Can we assume high impedance buffer as voltage buffer? Yeah, like I'm not sure what you're talking about saying voltage buffer. In digital circuits, I would say buffer is something which can transfer whatever voltage it has at input to the output, or instead of voltage we can take it as of logic. So if I have 0 at input, it should give 0 at the output. So that is one state of the buffer. If I have 1 at the input, it should have 1 at the output. So that is other state of the buffer. And the third state is not connected state. So it is kind of floating net. So consider, okay, I can show for more clarity. So if it is in third state, consider here as high impedance node. Okay. So you have very high resistance between the two connecting lines, and that's why the data on this side will not get transferred to other side, and that way the connection is broken and the tri-state buffer works fine. Okay. Okay. If everything is clear, I can move to the next slide, guys. And Tarun, can you please confirm this is fine? If this is what you wanted to ask or something else? Yeah, open circuit. Yeah. Yeah, Vikas, in other sense, we can say this. Oh, thanks, Tarun. Thanks. Okay. Hmm. So FPGA की designing तो हो गई. Let's come to ASIC now. Now you will be able to find the differences between designing an ASIC versus designing an FPGA. Okay. No, 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 no. It is not a logic zero circuit construct. So it is an open node. Okay. So it will be in high Z state. So if you ever do simulations of something like that, you will see a Z state there. Okay. So in Verilog, actually, we have four type of states. Okay. So it is let's say one, oh, shit. If it is a one state, it's a zero state, it's a unknown state, and it's a high impedance state. Okay. So the difference between these two is always confusing, but let me clear. X state is something that output may be zero or may be one. The simulator is not sure whether the output is 0 or 1, then it is showing X. Okay. But if it is a Z, then that means that the node is kept unconnected. Okay. And there is no current supplied to that node, and hence there is neither 0 nor 1, and it is a floating node. Okay. So it won't have any value. But yeah, if you come down to very low level, means very deep level, I would say, then you would see that the floating net, let's say I have a floating net here. Okay. So then, and I have a wire here. So then due to some coupling capacitances and resistances, this net can charge or discharge to some value, but that is a very rare case. Okay, got it? Circuit construct. Okay, let me clear. So let's jump into ASIC. So application specific integrated circuits. Okay. So what are these made up of? So compared to FPGA, where we had logic blocks, right? Similar to those things, as I already told, there is some building elements, right? So those building elements for ASIC are standard cells. Okay. So what all cells you have been studying so far in digital circuits and had no idea where to use them, how to use them. So that's where their use comes into picture. Yeah, thanks, Vikas. That's where it comes into picture. Like you have NAND gate, NOR gate, AND gate, NAND gate. So these all logic elements are kept together, okay, to form a design, and then the design is laid out, and then boom, you have ASIC. Okay, so you have some standard cells, you have some custom blocks. Okay, so metal layers are like you want to have, so let's say you want to do some routing between two blocks. Okay, so you have options of n number of metal layers. Okay, that depends upon the tech node which you are using. Okay, so you have some number of metal layers, and you can use that metal layers to route between those two. Okay, so but let's say you routed these two blocks. Okay, and now you have one another block, and you want to route like this. Now there will be a blunder, right? These blocks will not be connected because you have already crossed wires on each other. So how to keep this kind of routing? So the solution is to keep one routing in layer 1, let's say, and the other routing in layer 2. In that way, uh, you can route it exactly like this, and these two wires won't even touch. Okay. So it is like a hierarchy. Okay. So metal 1, metal 2, metal 3, metal 4. So these kind of layers which will be used. So if there is a crossing, you are seeing in design that metal 1 is crossing with metal 2. These two will never connect at this point because they are separated in 3D. Okay. I hope this is clear. And this is another topic I'm going in, but yeah, just for your understanding how these things come into picture. Okay. And the next thing is hard IP. So the custom blocks are like RAMs and everything. So what happens is like every time you don't build everything from scratch, right? So you have some custom blocks which can be modified a bit. Yeah, yeah, because something called wires. Wires are like, let's say you want to, you have some wire in metal one, okay? You have some wire in metal one, okay? And there is some other block uh, which has some wire in metal two, okay? Now you can't connect these, right? But you want to connect. So that's where the vias come. So via will transfer this metal 1 to metal 2. Hmm. That's another topic. I would say let's don't deviate, but yeah, it's good to have discussions. Okay. So next thing is so custom blocks. Everyone is clear, and the hard IPs are like hard IP mostly are called those IPs which everyone treats as a black box. So if I give you an hard IP, you don't need to touch it. You keep it as it is where you have fixed it place. Okay. So yeah, everyone in ASIC have some different kind of hard IP, but yeah, so some of the hard IPs are already mentioned. And okay, now you guys would say, okay, you talk about what is inside and everything, but yeah, yes, circuit construct. Very good. Yeah, that's it. Yeah. So that's why we are not allowed to use very high metal layers. Yeah, correct. Okay, IP is intellectual property. So IP consider as of a block. So let's say Vikas made something which has some function. let's say it adds, then multiplies, then divides, and then subtracts. It does all these operation and then gives an output. So Vikas don't want anyone to touch any logic inside this. He want everything as it is. Okay. Then he will make it this thing as in hard IP. Okay. So what IP is like, this is Vikas's design, right? So that will be considered as an IP, as in whole block. Okay, anyone don't need to know anything what's inside this. Just know ports, that what this is the input, this is the output, and the functionality. Rest all thing Vikas has taken care. Okay, that is Vikas property. If anything goes bad, Vikas will be tortured. Okay. So next thing is which I was jumping in is that okay, I told everything what's inside ASIC and how it is, how we are connecting blocks. Okay, we talked about routing, metal layers, everything. But what about the how to take input or output? So that's where the pad rings come in. Okay, so we have the pad rings and we connect the input and output to this. And why do we need pad rings, by the way? So we can cover this in more detail later. But in general, is like if you connect any output from outside, so it will have a very high contact resistance. Okay, so to compensate these things, we have these pad rings. So anything inside the IP don't get corrupted due to some input things. Okay, so that is the general idea. And okay, guys, let me know if we can jump into some other jump in forward. Circuit construct, Vikas, Bhuvneshwari, Tarun. Guys, let me know. Okay. Mhm. Okay, so this is just a simple block diagram that okay, we have this periphery IO boards. So these are very large in area also. And then we have this routing and then cells, routing cells, routing cells. So this is cell and we do the routing like this. Okay. So that is not a protocol, that is just something you can understand. Okay. This is how a ASIC chip would look like. The same way we thought of FPGA also. Okay. Okay. Please let me know. Can I move to next section? Because now things are going to get more interesting. Please let me know if you guys are live. Gautam, do you have any idea about GSM module? GSM module, Gautam, I know a little bit. I don't have all the internal architecture. How does it work? I don't know this thing. But yeah, if you want, I can research over that and we can have a session. We can have discussion. And yeah, and how come you get to this specific thing, GSM? Like you are working on it or something like that? Yeah, thanks, Circuit. Circuit, can I know your real name? Oh, okay. Thanks, Bhuvneshwari. Gautam, uh, that's one question to you. Please let me know. And yeah, we can definitely have session. It's a chip, man. It's already flat. It is a top view only. It's the way how you look it. You know a chip, right? It has a high area and less volume. Okay, okay. Let's jump to a very interesting session. Yeah, Bhuvneshwari. Thanks for helping out. Yeah, um, design flow. Please let me know, guys. I'm working on it. It's not. Yeah, that idea I have got them. Means I don't actually know the architecture inside it. Yeah, but okay. Maybe what you can do is we can connect offline and I can come up with some session. It would be very knowledgeable what you are working on, and then we can let everybody know. And I can also research on some GSM modules also. That is interesting. Yeah. Okay, Mahek Kumar. Yeah, thanks, Circuit. It's not a problem, man. You can join with any account. Yeah. Oh, okay, Vikas. Yeah. Okay, let's go quickly to the design flow. I hope this will be interesting because I find it interesting. Yeah. Means, yeah, you can. Okay, maybe I can give you guys my number. I'm sorry for bad handwriting, but yeah. Um, okay, I can directly comment here, right? Okay, so I have just dropped my mobile number. You can ping me on WhatsApp or something. Or if you are in group, then yeah, you can message there itself. We can connect. Okay. Okay, so let's start with the design flow. I hope everyone is with me currently. Okay. So in general, FPGA. So how is FPGA designed and how to use it? Okay. So in general, the flow looks same, that you have some specifications. Okay. So let's say Gotham wants to make some GSM IP, and before making it in ASIC, he wants to test whether the IP works correctly or not. But just not through the functional simulation. He want to actually test in hardware. Okay, because he knows the difficulty which can come up in hardware. Okay. So that's where he can use the FPGA flow. Okay, so what will Gotham start with? Okay, so he will have some specifications. Okay, that is a GSM IP, and it should support this bandwidth or should be fast enough to do these kind of operations. Okay, this should have some this area constraint or something like that. Okay, this should consume this much power. I don't want these many logic gates. I have a hard limit of using 100K logic gates or something like that. I don't want to use BRAMs. I want everything in logic. Something, everything he will come. Okay. And next, after he has the specification, he will do the behavioral model design. And after the designing, he will test it. Okay. He will test it using system C, C++, anything. Okay. And then uh, after he has some design and that is tested on some softwares like MATLAB or C++, then he can actually move into hardware and go into the simulations, okay, to verify this. Hmm? So simulations would be of two types. One will be the software simulations and one will be the simulations for hardware purposes, like which you can do with some tools, okay. So after that, just a second. Hmm, okay. So after the simulations are done, what will Gotham do is he will run a synthesis. Okay. So how this, so what is synthesis actually? So let's say I write a Verilog code. Okay. I have a .v file, but that won't directly go inside my chip, right? So the conversion of .v file to some netlist, hmm, to some netlist, that process is called synthesis. So that netlist will be dependent on platform. Okay, so for ASIC purposes, for ASIC purposes, you would have some gate level netlist. Means where you will have the GVs, which we say, huh? So where you will have some standard cells instantiated. Okay, and for FPGA, you will have the synthesis on the basis of these LUTs. Okay, so which LUT, how many LUTs you require, what to fill in. Okay, now coming to FPGA design, after the synthesis is done, now FPGA design flow actually start. Okay, synthesis is also a crucial step in FPGA design flow, but yeah, then it will say like, okay, I want to implement these things. Hmm? I want to implement the above synthesis in the FPGA board which user has specified. So it will go to the implementation step where it will translate the synthesis into some FPGA understandable format. It will map it, okay, and then route it. So here you guys know it will program the switches, right? And then it will generate the bit stream. And this bit stream has a lots of zeros and ones and then dot. Okay, and these zeros and ones, which these will be fed to the FPGA board, and the FPGA board will actually be programmed. Okay, I am passionate about electronics, but my projects are stuck. New project and it. Okay, yeah, Gautam, we can have this discussion. I could also help you getting some projects also. Yeah, we can have, definitely. I'm here to help you guys, man. We can work on, and I would love to work with you on some projects as well. We can have something. Yeah, yeah. Okay, Mahek Kumar. Okay, so everything, if everything is clear, can I move forward, guys? Mahek Kumar, Gautam, Vikas, Bhuvneshwari. Okay, so just yeah. Okay, thanks, Mahek Kumar. So yeah, thanks, Gautami. So just the same process which I said you in the previous slide. Here is a pictorial representation of how actual tools take into picture. Okay. So yeah, we will be taking up uh, these kind of projects which involves good tools like Quartus, Vivado. Those are all FPGA tools. Basically, these two tools are only famous, and we will use this Quartus and Vivado to actually synthesize our projects into some boards. Okay, so yeah, that will be a great learning. So here the tool says, okay, we are using an FPGA of Cyclone 5 family. Okay, and this is the code for FPGA. Okay, this is like just a name for FPGA, the same like you have the name Vikas or something. Okay, that in that way we have this FPGA code. Okay, no need to worry on that, and that has some more specifications. We can come at it later. Okay, in general, so what will happen is when you start compiling your design, so first what happens is after you write your Verilog code, first you will compile the design. It will compile the Verilog, whether your Verilog written, the written Verilog has good format or not. Okay, because we are humans, right? We can make mistakes. So there is a chance like our written Verilog code is not correct. Okay, the tool cannot convert, means the syntax is not correct, or we are having multiple loops or some linting errors, and many problems are there when you write a Verilog code. So first you need to run the compile design to check if the written Verilog code is correct. Hmm? And then you move to the functional simulations, and then coming back from the functional simulation you do these steps. First, you do the analysis and synthesis. So in this step, it will analyze the Verilog code and synthesize it into optimal format. Okay, and then these are the tools which we not until this. Okay, this until this we don't need to worry about what it is doing, what FPGA is doing, because these are all the tools algorithm on how to program the FPGA optimally. So after these steps are done, okay, then it runs the timing analysis, and that is of our interest. So as a designer, you need to know that what time does it take, what is the setup margins, what is the hold margins for your design. Okay, we can have some other session on setup and hold things also. But yeah, currently timing analysis is very important for designer, either in FPGA or in ASIC. But in ASIC, it is very important. In FPGA, like we can wave it off through some SDCs. We can reduce the clock frequency. It's just for testing purposes. So not a matter of fact. Okay, but the main thing which I wanted to point out, like, so after the synthesis is done and the process for FPGA is done, so it generates a programming file. That is the bit stream. Okay, and after it generates the programming file, you can use this button programmer to upload the bitstream actually inside the FPGA by connecting FPGA to your laptops. Okay, so here I wanted to say something in the flow summary, like in this flow you can see, okay, you written the Verilog code here, but that got translated into something which is utilizing 13 logic units. Okay, total 20 pins, 16 registers, 2304 memory elements. Okay, so these all things you can check for yourself where FPGA has synthesized. So there are many things in the tools which we can explore and actually check how the Verilog we wrote is getting synthesized in our FPGA. Okay, yeah, so that is very interesting. So if you see here, guys, PLL is also instantiated. Means one PLL is also used. So yeah, there must be some. So the name only suggests PLL RAM, right? And that's why it has too many memory bits. Okay. No, Bhuvneshwari. RTL design is not the ASIC design. Means you need to do RTL design even for putting the code on FPGA. But yeah, optimally, you don't need to optimize your design for FPGA because it's just for testing purposes. But yeah, you can check. So let's say, means I have also done in some of my projects on FPGA itself. So once I have given a code which is functionally correct and working, okay, and later I gave a code which is a bit optimized version written in Verilog. okay, which uses some less logic for the same functional equivalent of the previous code. And I have seen differences in these numbers. So yeah, it's a good practice to write the code neatly and logically optimized. But yeah, it is not very much required seeing on FPGA point of view. But in a ASIC, you need to have some very crucially optimized codes. Okay. I hope it is clear. Partial design is nothing, just writing codes in Verilog. And it's not that simple. You need to first come up with the design, what you need to make, how to make. You need to design the architecture and then. Okay. Mike Kumar, I am not able to get you what you are saying to go about developing softcore PLL in Verilog. I'm not sure if you are talking about this thing. Yeah, this is doing the same thing. Okay. And just want added this screenshot to uh, add some more things, like we have some power analyzer tool and some timing analyzer tools also available, which we will definitely use. And that is good, means that will be a good learning, that how much power your logic is using. Okay. Yeah, we will come up to these things definitely. Okay, guys, if anyone has any issues or problems or something else, then please let me know. And let me know if everything is clear also. ओके, कुछ बताओ भाई, कुछ क्लियर हुआ, कुछ समझ में आया? हाँ, we will have some session on SDA Vikas, static timing analysis. Okay. Yeah. Yeah. Correct. 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 Yeah. Bhuvneshwari. Yeah. This comes in ASIC cycle. I will cover this thing. I think that's right in front of your screen. Okay, because STA is static timing analysis, and the this is analysis of the static logics. Like, okay, you will have this logic change in this clock cycle and something like that, and you need to make sure that logic does not change when I am not expecting it to change. Hmm? So you have some clock frequencies, some specifications. So in STA, you have two concepts, setup and hold. Hmm? So setup is sensitive to frequencies, hold is sensitive to logic. Means setup also has the logic components, but yeah. So setup, uh, so you need to have a minimum frequency or a minimum time period such that the data from one flop to other flop gets transferred correctly. If you don't have it, then that is a setup violation. We can have a session and I can explain very clearly. Yeah, and it is asked many times in interviews. And yeah, it is a very good concept and it is a very deep concept to learn in. It's just not the setup and hold. You have many lots of things. Okay. Yeah, I think my Kumar, it is coming slow. I'm not sure. I will try to fix it on the next session. Okay. Let me know, guys. Shall I start with ASIC? Yeah, Bhuvneshwari. Yeah, causes metastability. Yeah, you guys know a lot of things, man. I think I can learn from you guys. Thanks. Okay. Okay, so let's start to ASIC part. It's already late now. So system space. So just like any other design, system specifications we design. Okay, and after that, uh, we design the architecture. Okay, like we write the ideal codes, we create the analog IPs or everything which is required according to the system specifications, and then we do the functional and logical design. Like so, this involves functional and logical simulations also, and compare the design to if it is matching the architectural design or not. Okay, and then we have the circuit design, like we need to place the standard cell and everything like that. Okay, and then we have a very important step in ASIC. We talked in the first session as well, physical design. Okay, that is the heart of VLSI. And so physical design involves many steps like partitioning, floor planning, power planning, placement, clock tree synthesis, routing, timing closure. So if we go into the depth of these things, it will consume a lot of time. But yeah, on a top level view, physical design is constructing a design on your chip. Hmm? So let's say you have a chip of some x cross x area. Okay, then you need to do first floor planning. Okay, this IP will come here, this IP, this number of IPs will come here, this will come here. So you have the floor planned. Okay, and then you will have some power rails. Okay, and then you will do the power planning. Okay, this IP uses lots of power, so I will put it here, and the other IP I will put it here, so that there is no heating, coupling, anything like that. Okay, and then we do the placement. Yeah, that is also dependent upon everything. Hmm? So placement, and then the main thing, very interesting, it is a very interesting topic and lots of research is going on, and we have many methodologies for clock tree synthesis. Okay, so let's say I have IP here and IP here. So what will happen is if the clock comes in and it goes to here also and here also, naturally we will have more delay due to this wire length to the clock of this IP. But we don't want, because there may be a chance that the data from this IP and this IP would be given to some other IP which would be utilizing it. So it will receive one data faster and other data later. And that will be an issue, right? So we should not do this. And that's why we have many different, I would say, architectures, or we have this problem statement of clock tree synthesis, how to do it. So in general, we can say that we add some more delay in order to compensate this wire delay, and we get the data in time. So that is how clock tree synthesis is done. Okay. And then the routing, which I already told, I want to connect this IP to this IP. So that's where the routing comes into the place. And at the end, and that's the most important thing everyone talks about, that is the timing closure. Okay. So you need to close the timing, and Vivek, that's the thing where STA comes into picture. Okay, Bhuvneshwari, yeah, Sankar sir taught me a lot also. Yeah, yeah. Okay, and then after that, the physical design is done. Then we have a physical verification. And if something fails in some physical verification, we are again back to the functional and logical design. And then again, the process is repeated. Okay. So this is a loop. So architectural design and this functional design, and there is a self loop also, that verification fails, you again design, fails, again design, and then you come here. And if everything goes fine, we go to fabrication and finish the chip. Okay. So if everything is clear, I would move to some more details. Guys, let me know if you are exhausted, then we can have this covered in the next session, or if you want to continue, I am very much happy to continue this session. Bhuvneshwari, Mahak Kumar, Vikas, Gautam, please let me know. Yes. Okay. Yeah, Bhuvneshwari. It is very important. Uh, yeah, Mahak Kumar, thank you. Okay, we can continue on the command of Mahak Kumar. Okay, so just top level diagram again. So these all things you know, I don't need to cover it. Okay, so in physical design, it starts with synthesis, as we already talked, that you have a Verilog code, then you convert it into netlist. Okay, and after you have the synthesis, so you know how much area in general it will take. Then you can start with floor planning, placement and optimization, and this is a repetitive process. You optimize, then you do the floor planning, optimize again, floor planning, like that, and then you do the clock tree synthesis and do the placement and routing. Okay, and in parallel to this, there is everything related to STA, means timing analysis, crosstalk analysis, and IR drop. So maybe crosstalk analysis in general is, let's say you have a wire 1 and a wire 2. Okay, and this is having a logic 0, this is having a logic 1. So if at all they have a crosstalk, okay, जैसे कि मान लो विकास और भुवनेश्वरी क्लास में है, आजू बाजू बैठे हैं, but the teacher won't want them to talk, right? Because Vivek would have one opinion and Bhuvneshwari would have another opinion, and they can cross talk, and someone can influence someone, and teacher won't don't want that. Okay, so that is a cross talk in general. So I don't want as a designer कि मेरे एक वायर में 1 फ्लो कर रहा है एंड एक वायर में 0 फ्लो कर रहा है, और कुछ क्रॉस टॉक की वजह से इट गोज फ्रॉम 0 to 1, तो फिर तो मेरा डिजाइन खराब हो गया ना. I don't want that. So there are many methodologies to prevent crosstalks also. So crosstalk analysis is done, and then the feedback is again sent back to routing, obviously, because it is among the wires. Okay. And similar to this thing, there is something called IR drop. So let's say you have a power domain VDD here, and you have some block here. Okay. So this wire, which is connected from VDD to this block, will have some resistance R, right? And let's say it is having some current I. So चलो भाई, शंकर सर ने पढ़ाया है सबको, तो let me know what is the voltage which is coming here. Let me know in comment section. ये अभी तक कुछ रिस्पांस नहीं आया। आई थिंक कमेंट मेरे में देर से लोड होता है। ठीक है। Yeah, thanks Bhuvneshwari. Yeah, exactly. So, yeah, yes, yes, Vikas, yeah. So, due to this IR, ये VDD अपना कम हो गया, राइट? लेट्स से मेरा 1 वोल्ट पे कुछ चीज चल रहा था, नाउ इट इज जॉट डाउन टू 0.9 वोल्ट। या थैंक्स मयंक कुमार। या एग्जैक्टली करेक्ट। VDD माइनस IR, तो अब ये 0.9 वोल्ट पे चलने लगा, राइट? एंड ड्यू टू दिस चेंज इन वोल्टेज, मेरा जो आईपी के अंदर के कंपोनेंट हैं वो भी 0.9 वोल्ट पे चलेंगे। एंड एज यू नो कि जैसे ही वोल्टेज कम होगा द स्पीड विल रिड्यूस, है ना? एंड द स्पीड विल रिड्यूस, तो भाई मेरा टाइमिंग खराब हो जाएगा, एवरीथिंग विल break down eventually. So IR drop analysis is important, and okay, IR drop rahega, but we will close the timing for these IPs such that we take in consideration of these IR drops. So we want to limit the IR drops to some minimum value, और फिर उसके लिए margin set करके अपन reduce करते हैं. Okay, that's a practical thing. And this feedback is sent to the routing team because ये routing तो उन्होंने ही करी है. Okay, so that is how these things are done, and then we do a parasitic extraction and layout verification. तो layout verification में it's a very good concept. मतलब एक होता है LVS और एक होता है DRC, है ना? सो LVS इज लेआउट वर्सेस स्कीमेटिक। सो जो आपने स्कीमेटिक में बनाया है वो आपके लेआउट में दिख रहा है कि नहीं मुझे, दैट इज वन चेक। तभी तो वेरीफाई होगा ना कि भाई जो मैंने बनाया था वही जा रहा है कि कुछ और जा रहा है। एंड DRC आर सम, देयर आर सम सेट ऑफ रूल्स कि भाई दो वायर्स के बीच में इतना ही डिफरेंस होना चाहिए एंड समथिंग लाइक दैट। सो for that we have some rules, and these rules needs to be maintained, and that's what the DRC check do. Okay, and at last we have the GDS and we give it for fabrication. इसके बाद से तो सब fabrication fab lab का चिंता है। The synthesis tool used for FPGA. Yeah, yeah, Mahek Kumar, the synthesis tool used for FPGA and ASIC are not the same. Because in FPGA we wrote for very optimized synthesis. We have lots of logic elements, and the synthesis needs to be synthesis is dependent on the tech node which we are, okay. तो हर FPGA बोर्ड के लिए अलग टेक रहेगा. Yeah, so it is independent, I would say. For ASIC design, we use very advanced level of synthesis tool, which are not required at FPGA level. Okay, okay, let me know, guys. आगे बढ़े. We're running out of time, I guess. Okay, so this is just a simple flow of ASIC design. तो आपने डिजाइन बनाया, ठीक है ना? फ्लोर प्लान बनाया, टाइमिंग मोड सेटअप किया, उसके बाद प्री CTS फ्लो. प्री CTS फ्लो, CTS मींस क्लॉक ट्री सिंथेसिस. ओके, सो बिफोर CTS you do, okay, so there is one more thing. oh, ये जो भी मैं बता रहा हूँ ऑन अ स्टूडेंट पॉइंट ऑफ व्यू ये सारी चीजों में जॉब है भाई. From specifications to design to simulations, logic design, functional and logic design, verification, physical design, synthesis, floor planning, everything in this list has a different team, okay, working on even this also. and this also. So you have lots and lots of opportunity in VLSI. So देखो बहुत है. You have lots of thing to learn, and you can fit into anywhere. Okay. So here also you can see a job opportunity, scan definition. So क्या होता है कि आपने डिजाइन बनाया, बट after it comes in silicon you can't change it, okay, but you need to verify whether it is working fine, and you need to debug, okay, if it is working fine or if it is not working fine, what is going wrong, क्योंकि इसमें तो मैंने 100 चीजें डाल दी. I want to identify कि कौन सी चीज खराब हो रही है. So for that we have this scan thing, okay, we insert the scan change. So scan change कुछ नहीं होता है, just at the flops we insert some मतलब instead of let's say there are इतना ही डिजाइन है, एक मान लेते हैं बहुत ही छोटा है ऐसे क्या, इसमें दो फ्लॉप है, ओके. So there is some combinational logic between that, and this is the input and this is the output. So ये यहाँ से input से जाएगा and this will go from some logic, and this will take output from this block. Okay. तो अगर ये लॉजिक में कुछ भी खराब हो रहा है, लेट्स से टाइमिंग ही खराब हो रहा है, सेटअप मीट नहीं कर रहा है कुछ भी, तो वो कैसे पता चलेगा? यू कैन बाईपास दिस थिंग, ओके. सो स्कैन में क्या करते हैं, एक स्कैन इनपुट इंसर्ट करते हैं. सो इन स्कैन मोड व्हाट विल हैपन इज, जो भी मैंने स्कैन इनपुट पे दिया है वही ये फ्लॉप का आउटपुट होगा, एंड दिस विल डायरेक्टली बाईपास टू द स्कैन इनपुट ऑफ सम अदर फ्लॉप, और फिर ये डेटा बाहर आएगा. तो अगर मैंने 1 दिया है तो 1 ही बाहर आना चाहिए, करेक्ट. अगर नहीं आता है देन देयर इज समथिंग रॉन्ग, एंड देन वी कैन से कि इधर पे कुछ दिक्कत है, यहाँ पे कुछ दिक्कत है, लाइक दैट. So that is scan thing, okay. And okay, cell placement and pre-CTS optimization, then we do the timing, and if it is not met, again do everything. So for timing now, about अपन ने scan भी डाल दिया है, तो for scan also we need to do the timing, okay. Now after the timing is met, we go for the CTS and do the CTS flow, and then do the timing again and fix it, and if it is fixed then we go to routing, and then again we do the timing. इसलिए विवेक, you were saying right कि timing मतलब STA बहुत, तो as you can see at every stage you will have a timing, okay. So STA is very important for us as an engineer. So this was just a nutshell ki how flow in ASIC works, okay. Okay, so let's have a small comparison. So ये slide तो it's a self-understood slide, but yeah, okay, you can have it. Guys, please let me know you are following through or not. Okay, so the basic difference in ASIC and FPGA comes right from the after the design itself, okay. In FPGA we don't need to debug anything, so we don't need the DFT insertion logic, okay. We don't need to perform the STA and equivalent checking again and again, because we are using the synthesis tool of the FPGA itself. There is very less chance to do the that the synthesis tool may optimize your code to something else, okay. So okay, equivalence checking, we missed it. Equivalence checking is what you wrote in HDL versus what came out of synthesis, okay. So you want to check whether these two things are same. So for that you need to do a equivalence checking. So there are many tools for from Synopsys and Cadence, namely conformal and I guess formal, something like that. Okay. So conformal is from Cadence. Okay. And formality is from Synopsys. Okay. Yeah. So that do the equivalence checking between the synthesized module and the Verilog code which you have written. And that is very important in ASIC flow because you need to make sure what you are giving to a PNR engineer, is he getting the correct thing which you wrote in code. Okay. But in case of FPGA, there is nothing like that. Okay. Because whatever you wrote in HDL, it will directly get synthesized. It won't even optimize much. Okay. And then we have the placement and routing, and after that we do STA here because we know nothing can fail after synthesis or something like that. Okay. And then directly we download and verify the circuit in FPGA. But in ASIC we have this much long process and we have already gone through everything. So yeah, that's why the cycle for FPGA is very its turnaround time for FPGA is very less and ASIC is very high. Okay, so let me know, guys. I guess many of you left. Bhuvneshwari, Mehak Kumar, Vikas. Guys, please let me know if you are following through. Gautam. Okay. 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 So with this, like more kind of technical session is done. Now we can just have some comparison between ASIC and FPGA. Okay. So on the way, on the yeah, thanks Vikas for giving the feedback. On the coming to the timing, FPGA have very lower frequency, and that's why because we don't need to worry much about STA in FPGA. But ASIC runs at very high frequency. Okay, वेस्ट करो मतलब तुम्हारा खुद का ही प्रोसेसर कितने 2-3 गीगाहर्ट्ज पे चलता है ना. तो क्वालकॉम के नए नए प्रोसेसर आए हैं 2.8 गीगाहर्ट्ज देते हैं, कुछ कुछ तो ओवरक्लॉकिंग पे 4 गीगाहर्ट्ज भी दे देते हैं. सो एसिक है इसलिए देते हैं. You can't expect same speed from FPGA. Okay. And critical paths, these are in the timing. So just to have a view, like obviously FPGA में दूर दूर placed है ना सारी चीजें. So there is high delay due to routing. क्योंकि routing उसकी fixed है, ये यहीं से ही जाएगा. But इसमें routing अपन खुद से manage करते हैं ना, तो it is very optimized. And same with the power consumption, वो fixed है. So that is not an optimized thing for your design. So it will have a very high dynamic and static power consumption. But in ASIC, you employ many different methods like clock gating, low VDD domain, etc. Okay. So clock gating is also one very interesting topic. Yeah, we can also have something on this also. Okay. And area efficiency, obviously, like FPGA will have more area because it needs to accommodate for programmability, right? Instead of that, the ASIC has denser packing and custom floor plan. Okay. Coming to most important thing on business point of view. So in FPGA, the upfront cost, like the cost for making it is means almost none, like okay. But for ASIC, it is very high. It's in 100K of dollar. Oh, that's a huge number. Okay, but per unit cost for FPGA is high compared to ASIC. But if you look at a picture of overall cost, so for FPGA the cost is quite lower than ASIC. Okay, And the best use case is like low volume production, okay? Because if you will have a high volume production on this cost, then obviously the FPGA cost will be very higher than ASIC. And that's no point on using the FPGA. Okay. So total cost efficiency, obviously. For sales purposes, if ASIC is excellent. If you want to like make your IP for everyone to use, let's say Gotham wanted to use GSM block. So for that he will make ASIC, right? He won't make an GSM in FPGA. That's useless. Okay. And debug and testing time and time to market. Time to market मतलब तुमने जब डिजाइनिंग चालू करी तब से मार्केट में कब तक आ पाएगा. Okay. So debugging tool, okay. So FPGA have very cool things called signal tap and logic analyzer, in which while it is running on FPGA, you can program some signals directly through the software. Okay, so that's a very cool thing. So you can debug the design there itself, but that thing is not available in ASIC, obviously, because it is not a general purpose thing. Iteration speed, obviously, it is fast. It does not take lots of time. You can make one design and the other design. It's very quick to test. But this ASIC requires is very slow. You need to run respin and see it's week or month. Okay, that's why we as an engineers are crucial. We spend a lots and lots of time on this ASICs, and that's there is no way we are going anywhere. Yeah, Mehak Kumar, I may not totally agree with you, but yeah, in ASIC, the synthesis tool optimizes everything. Either it's combinational logic or it's sequential logic. Everything it optimizes. Okay. Yeah, so development flexibility, you have high programmability in case of FPGA rather in case of AC. And bug fixing cost is very low in FPGA. Yeah, so that's why we use in total FPGA for testing purposes and ASIC for marketing purposes. Okay, industry application. So in industries like aerospace and these things, we need some reprogrammable systems. So where we use FPGAs, and where we have some hard specifications, we can use ASIC. So that's just a simple table. Okay. So it's having the same thing overall. In AIML also, where we need multiple iterations and prototyping and these things, we use FPGA only. Okay. But where we want some chips or some processing units or something like that, we will definitely use ASIC. Okay, so that's the that's everything from my side. Any thoughts which thing to use, ASIC or FPGA, which you will use now? Guys, please let me know in comment section. And please give if any suggestions on next session, on what do you want next session. And do we want some session more comprehensive like this or more crisp like the previous session? Relevant question. Windows. Oh, okay. Bhuvneshwari, analog engineers comes into picture in custom designs. Okay. So here, if you see, right, There are some circuits designs, okay, and in the this logical designs also we have some custom blocks, okay, and in addition to that, the building blocks of our ASIC, the building blocks, these standard cell designs. So these designs are also done by analog engineers. So NAND gate is not what we digital engineers look like this. It's not exactly that. It's made of PMOS and NMOS. So this is designed by some analog design engineer. Okay. Yeah. Yeah, Mehak Kumar, that's correct. Like, yeah, Bhuvneshwar is saying FPGA, Vikas is saying ASIC. You guys gonna have fight today, huh? Yeah, Mehak Kumar, yeah, FPGA for prototyping and ASIC for large scale. Yeah, that's true. Okay. But yeah, I personally as a student would prefer FPGA. I would, yeah, I don't have any business to run on. Yeah. For learning purposes, for exploring, we can use FPGA for sure. But yeah, it is good to have knowledge on ASIC flow. And in the sessions from the course, we will explore both the FPGA and the ASIC flow. We'll have some projects on FPGA and ASIC flow as well. Oh, who gets paid the most? It depends. What work do you do? But yeah, there are engineers who work on FPGA and there are engineers who work on ASIC. But saying it percentage wise, only 10% of engineer work on FPGAs and 90% of engineer works on ASIC. And on basis on the saying on fronts of salary, both the engineers I would say earns the same because they both do similar efforts. Okay, then RTL design goes both analog and DV. Yeah, RTL design goes in basically those are digital engineers and DV. Analog designs are the custom design. I would not say those as the RTL because RTL is the register transistor logic. So we use the cells or the custom blocks in our IP from analog guys. So consider analog guys on the top. So first they design the custom IPs and then the RTL designers use them. Okay. Have any ideas? Startup in no man, Mahek Kumar. It's just been a year I joined the industry. I don't have any startup idea currently. But yeah, means there are many things to explore. First, I think we should explore what all things are there, then we can think of these things. Okay, if you guys have any other questions, if not, then we can end this session. Let me know, guys, Vikas, Bhuvneshwari, Mac, Kumar, or anyone who is live. I don't see any comments. Mac Kumar, I shared my WhatsApp number in the chat itself. Maybe I can put it here also once again. And if anything else, if you are not able to contact me through WhatsApp, you can anyways connect on LinkedIn and we can have. Okay, thanks Vikas. Thanks for joining. Okay, so if nothing else is there, then we can close this session, right? Thank you guys for joining, and I hope you liked the session. And if you guys liked it, please comment what other session can I come up with. Okay, I get it. But RTL codes in hardware are gate flaw with transistors deep down. Huh. Yeah, got it. It has to go through the analog design. Yeah, not the RTL is done means it's a instantiations. Like okay, so let's say some analog engineer has designed some cells, right? So RTL designer can use this cell n number of times in his code directly with the connections. Trusting on analog design engineer that okay, he has made the cells according to the functionality and I can use it. Yeah. And on DV for verifying, DV just need the RTL code. He does not need what all standard cells we have in the design. He just take up the RTL code and synthesize using the tools. Okay. Means not synthesize, simulate it using the tools. There are many DV tools which does the simulations. So in simulation, there are two things like gate level simulation and RTL level simulation. Okay. So in RTL level simulation, you just take the RTL code, the Verilog code, and simulate it. In gate level simulation, you use the cells which are designed by the analog engineers and simulate them. Okay. I hope it is clear, Bhuvneshwari. Okay, Mahek Kumar, next session, holds and hands-on session. Okay, hands-on session. Yeah, I will try to take it. Uh, if possible, yeah, I will talk and I can try to take it because that would require some interactiveness. Okay, I can check. Mahek Kumar, sure. That's a good idea. Thanks. Yeah, because I have sent the number. Yeah, thanks a lot everyone for joining. एक बार confirm कर दो if I can close the session or you have any questions. And Bhuvneshwari, is it clear? Yeah, okay. Thanks Bhuvneshwari. Yeah, thanks a lot. Thanks guys. Thanks for this much good response. I really liked it. Okay. Okay guys. Thank you everyone for joining and जो भी अलग से देख रहा है live आओ we can talk more. Okay. Thank you. Thank you guys. Okay, closing the session. Yeah. Yeah, Mahek Kumar, I have shared my number. Is it visible in the chat? I have already shared actually. For, uh, yeah, thanks Vikas, thanks. I've shared it again. Please let me know if it is visible. Or maybe I can. Yeah, okay, I am into DV. Was thinking ASIC is. Yeah, yeah, Bhuvneshwari. Yeah, we can discuss more about DV also. If you want, yeah, we can also connect. You can also connect offline, means offline also if you want to know more, or we can have session based on your suggestions. Yeah, if you guys have any suggestion, you can any day comment on the video and then I can come up with session. No need to comment on live. Yeah. Thank you. Thank you guys. Yeah. Now visible. Okay. I prefer. Okay. No man. Analog designers are also great. We have to show them respect. Okay. 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 Thanks, Vikas. Thanks, Bhuvneshwari. Thanks, Mahek. Okay. Bye. Bye, guys.